First of all, ISAC in 6G is very broad and general. So I'm not going to tell you what ISAC in 6G is. So that's why I added this HHI perspective. So it's not a typical scientific talk. I will just basically, present. I will present what is interesting for us at HHI and TU Berlin, and then you can see, the collaborators. I am here more or less. I mean, the least important person, and so that's I give some kind of overview of what we are doing at HHI in this area. First of all, what is important to understand for the talk that we, in the context of integrated sensing and communication, ISAC, we differentiate between bistatic ISAC and monostatic ISAC. So this is for those who are not familiar with, ISAC. Bistatic basically means that we have distant transmitter and receiver. They are not collocated. So this is just, the native setup for communication. And then the idea is to use the communication infrastructure to provide additional services related to sensing, right? And here, big challenge is synchronization and coordination between, for example, different base stations. Here we can have scenario uplink, downlink, but I think that for the talk, it's not so essential. And then on the other hand, we have monostatic ISAC. In this case, transmitter is collocated with sensing receiver. And here, of course, the advantage is that we have a perfect synchronization, more or less. And also full signal availability, because the sensing receiver knows what the transmitter transmits. But there's a big challenge, self-interference. We can have a strong self-interference, and this is something we have to cope with. Okay, so usually such talks also say something about use cases, but here's maybe one use case that also should illustrate or just maybe show some kind of interesting scientific problems. Here you have this is a video. You have something. It's collaborated robotics, formation control, and target tracking. You can see here this vehicle, and all the robots need to follow him, and then also form a formation. So, and the nice, okay, what I am trying to say here is that the following, that in order to realize something like this, we have here a combination of perception or maybe localization, control. We have here unstable system. These robots are unstable, so you need some kind of local controller, but also task-oriented communication, because they need to reach consensus. So they need to form something and then follow, this guide, and then also avoid collisions. So basically, people say, to realize such a use case, you need perfect localization, which is not true. You don't need this, and this might have impact on how we just, define performance metrics for sensing. Okay, so anyway, if we talk to industry guys, they say we have to start with something, loose integration of sensing and communication. So you can buy radar sensors; they are really cheap, and add to the communication infrastructure to do some kind of communication and sensing. If you ask researchers, then of course they are interested in something, joint waveform design that optimize the trade-off between sensing and communication. Okay, so first of all, I think that there's something, gray zone, and there is something, you can use 5G NR-based ISAC, which is evolutionary approach, right? So here the basis is the OFDM waveform. This is what we use, and also 3GPP already settled OFDM as the 6G waveform, right? So this is, to my understanding, all discussions at 3GPP related to ISAC, they assume OFDM waveform as a basis for this. Okay, and here there is even, paper, Giuseppe here is co-author, cyclic prefix or FTM is even optimal for this kind, to achieve the best trade-off between communication and sensing under certain assumptions. And of course, it also depends on the metric you consider. Okay, so what does it mean? I mean, here I would like to illustrate that, this is low-hanging fruit. And we have developed a demonstration platform, and this is also, I am showing this, to invite if somebody is interested in some kind of collaboration. So basically, for example, in the uplink, you use pilot signals and channel state information to do sensing on top of communication, right? So here we have NVIDIA Aerial 5G, and which is basically hardware accelerator using GPUs to to use channel state information to extract information that is relevant for sensing. Basically to extract delayed Doppler maps, right, in real time. And this can be, we showed this last year at this Berlin 6G conference. So what you can see here, a channel frequency response for 4 antennas. We have a system with 4 antennas. And here, this is just, for the blue one, for 1 antenna. And then you can see here distance or delay Doppler map. So you can see, okay, the object is not moving. And then you can see here different multipaths. And this is just, this 64 QM constellation. So it's possible to do something. But, okay, I assume that this is, not surprise that you can do some kind of sensing, but there are some challenges. And this is, I think, an important slide here. First of all, we use, this DMR-based channel state information to do sensing. So it means that the sensing can be performed only when user data are sent, which is a big problem, right? So that's why, now the question is, which signals we can consider to provide sensing, even if the data is not sent. The second thing is, okay, there is a problem with the synchronization between transmitter and receiver. And here you can see that if you have this sampling frequency offset, then here, this is, what I showed on the previous slide. You have a EU that is not moving, everything is stationary, but what you observe without this S of O correction, you see delay Doppler map that is smeared out, and you cannot do much, based on this delay Doppler map. So, but of course, there are techniques to correct this, and then depending on what you do, you can just, you can achieve what you, without perfect synchronization, you can achieve the desired result. Okay, so then, for example, here, another problem is that EU is not, the position of the EU is generally unknown. Okay, so if it's unknown, of course, you cannot do ranging. Maybe you cannot reconstruct the geometry of this room and things like this. But still, and this is, I think, important, to emphasize that still you can use it for sensing. I have one simple demo. There are many use cases that, where people are not interested in localization, they are interested in detection and so on. So still without, this information, you can use this technology to detect some events. Okay, there is limited bandwidth below 100 megahertz. Okay, so you cannot do many things because the bandwidth is not big enough. So that's why we are going to high frequencies, even sub-terahertz and terahertz, where you have 4, 8 gigahertz, and even 50 gigahertz if you go towards 1 terahertz. So you can do sensing for spectroscopy and things like this. And then here we have a collaboration with our colleagues from the Charité. Okay, and then of course you can be potentially in motion, and then of course this will also cause some problems, and this is I think also a challenge. Here there are two things. This is just one simple demonstration that you can use this sensing for detection. Here you can see Peter, he blocks, this door. And then, of course, this has impact on the channel impulse response. And then here, there's another thing that is bistatic, but also using side link. Yeah, so there's a side link. And then one example, and then, for example, doctors from the Charité are highly interested in this to detect whether a patient is a bat or not. Okay, so this would help. Good, so now let me talk about a little bit about another topic, which is beamforming for monostatic sensing. So I think that beamforming is essential for sensing, especially if we go to higher frequencies. And then monostatic sensing has some advantages, especially, you have this perfect synchronization, and then you have full availability of the transmitted data because transmitter and sensing receiver are collocated. But there is a problem with self-interference. Okay, and this is illustrated here. I mean, first of all, the self-interference can be much stronger than the signal you are trying to detect. I mean, 100 dB can be, and then of course you cannot do anything. This drives your LNA, I mean your amplifier and the saturation, and then this causes nonlinearities, distortions, and things like this. So this is something you have to avoid. And usually you have this passive decoupling between the transmitter and receiver. But after the amplifier, you have AD converter, an analog digital converter. And then, of course, if the signal is still stronger than the signal you're trying to detect, you have to, first of all, avoid saturation of the analog digital converter. So that's why you have this automatic gain control, and you have to avoid this. So it means that you cannot amplify the signal you detect to exploit the whole dynamic range of the AD converter, right? So that's why, I think that in order to enable this monostatic sensing, you need active cancellation using RX beamforming. Not only, receive beamforming, but also some kind of combination of transmit and receive beamforming. And then, of course, in the end, after that, you still have some kind of residual interference. And this is something you can cope with in the digital domain. There are methods, DSP residual SI cancellation, and here there is a paper of us where we use kernel-based machines to reduce this residual self-interference in the digital domain. But here the focus is on the analog beamforming, on hybrid beamforming. Okay, first of all, I mean, what we did is we had the first paper, and then we have some kind of idealized assumptions. And this is, the scenario we are considering. First of all, you can see here you have a transmitter, you have here a receiver, a sensing receiver, and then you have here a communication user, you have a probe target and unprobed target. So you try to illuminate, of course, I mean, you try to communicate and illuminate this probe target, but of course, you have to avoid some kind of interference from the unprobed target, okay? So, and the problem is here, what we did is that we have this low SLL beamforming. Basically, we try to maximize this ratio between the power illuminated in this direction of the probed target and minimize the side lobes to reduce the misdetection. Okay, so I mean there's a difference to MMSE-based approaches because in this case they try to estimate this, okay, have some kind of lower bound and upper bound. We are not interested in upper bound. We just try to increase the power or ensure that the power in the main lobe is above some threshold, and then that the unprobed side lobes, the side lobes are small enough. Of course, then there is some kind of power and cell interference constraints. You have, power constraints. You have constraints related to the saturation at the receiver side, and then you can also try to impose the constraint that avoid the self-interference. But of course, I mean, the problem in general might be unfeasible. So that you have to develop algorithms that can cope with such problems. You can relax this. And then basically what we use this projection on closed convex sets methods. And then we also use this, so it's like, you have this fixed point algorithm, and then we perturbate this fixed point algorithm to achieve some additional goals. Okay, and this is here SNR. I mean, the classical SNR constraint, to ensure some kind of communication quality. So, and okay, so in this theoretical work, what we can see that the gains are really impressive. So you can have 33 dB extra suppression. I mean, in this simulation we considered. And so it means that, for example, you can extend coverage by factor 6, or you have better ADC resolution by 5 bits. Okay, so this is, I think that, this shows that there is a huge potential for some kind of performance gains. And here you can see what it means in terms of detection. You have here this receiver operating ROC curve. I forgot a characteristic. And then you can see that here you have the methods based on MMSC, and here you have this method that exploits the information available at the receiver. Basically, the problem, we cannot solve this optimally, but what we can solve optimally is we just divide this problem into sub-problems, and we use these alternating techniques to improve the performance in every step. Okay, so, but if you go to practice, then of course there are some assumptions, and then they are not satisfied in practice. First of all, if you have hybrid digital analog beamforming, you don't have the whole full channel state information. This is one thing, and then you have to cope with codebooks. And then also you have multipath cell interference effects. So it means that there is not only the direct path from the transmitter to the receiver, but also you can have multipath components due to other objects, so that the SI channel is a multipath channel. Oh, this is okay. So anyway, there is a paper on this where we just use our framework to adapt the theory I presented on the previous slide to tapered beamforming of phased array codebooks to meet specific SIR targets. And then, okay, so what is, I think, nice about this, that we have some bounds and guidelines how to design the whole system in order to ensure some sensing performance while preserving 5G and communication quality. Okay, so I will skip this slide because it takes some time to explain this, and but I refer to the paper I presented. So maybe the last topic is beam pattern synthesis. I mean, here the problem is that, for example, if you go to higher frequencies and you use beamforming, you would like to have some kind of desired beam pattern, because you have communication users and then you have sensing users, and then based on this you have reference covariance metrics, you have some kind of communication criteria, and then would like to generate dual functional waveform that satisfies some criteria, right, for communication and sensing. So this is this science fiction from the industry point of view. So that here the goal is to come up with a new waveform to do this integrated sensing and communication. So I mean, here this is a simple simulation why we need very fast algorithms to compute these beam patterns. For example, depending, if you have high mobility, you may want to control the beam width depending on the mobility, because just if you have narrow beam, so it might happen that you cannot just point in the direction of the target. On the other hand, for example, you may have you may want to generate two beams. One is for communication, and then you use the second beam for sensing. And then you have to permanently compute new channel covariance matrices or corresponding dual waveforms. And for this, you need very fast and efficient algorithms. And this is what we did. Basically, we formulate the problem as a matrix narrowness problem. So you have some kind of target beam pattern matrix, and then you use this steering vectors and put it in a matrix at different angles, and then you try to minimize this Frobenius norm, which is the distance between the target beam pattern and the beam pattern that corresponds to the channel covariance matrix of the signal. Okay, so this is the method, more or less, and of course we are better than these two methods proposed in these two publications. Especially what I would like to emphasize is the complexity. If you have 16 antenna elements, then this is the computer you use, and this is what you need to solve the problems proposed in the literature. So we have huge performance gains in terms of complexity and speed, which was our original goal. But also we are better in terms of some performance metrics I introduced on the previous slide. So let me say only just 2 minutes about D-band sensing. So there are some front-end development. Maybe one thing, because I am not hardware guy, but it's analog processing. It's based on Rotman lenses, and you can generate very efficient narrow beams and then switch between them. And then okay, so here you can see what we can achieve. We had a carrier frequency of 160 gigahertz, and at the moment we have 4 gigahertz bandwidth. So this is, when compared to FR1, 100 megahertz, it's a huge bandwidth. And then, of course, you can do much more, especially in the context of medical applications, right? And and then we had this demo last year. So basically, it's integrated sensing and communication. We have, here data rates of 5 gigabit per second, and then sensing at the same time. And then, I mean, integration is quite easy. I mean, or straightforward, I would say. Here you have, Frank-Zador of two sequences that you use, to sense and to construct this delayed Doppler maps. The question is, what is the use case for this? At the moment, we are looking for interesting use case. So if somebody has an idea what we can do with this technology, where you need, 5 gigabit per second and at the same time sensing or ranging with precision below 3 centimeters, then you can contact me. Thank you for your attention.
Thank you very much for this very interesting talk, from which we can see several inspiring application-oriented examples. I believe there are many questions from the audience.
Not so many. Okay.
Hi, thank you for this very interesting talk. Maybe you can say a few words about sensing and communication as you use it, or the same wave and the same data transmission for both. What kind of problems, or if you have more the focus on sensing, what happens with the communication and vice versa, because both in a very best transmission is probably not possible in a good way. So what are the impacts?
Okay, so there are theoretical works on this. I mean, there is this paper of Giuseppe Caire. They investigate the trade-off between sensing and communication. And then basically, to my understanding, is there is an inherent trade-off, right? So, and this, okay, I didn't have time, but also in some simulations, you can see the trade-off. I mean, especially if you, when it comes to beam pattern design, I mean, here there are no information theoretic metrics, right? We give a target, a beam pattern. And then, of course, if you have, for example, users, communication users, and you increase SNR, desired SNR, so you can see that the power illuminated to probe target decreases, right? So you can see this effect as well when it comes to antenna design. So basically, I think that at the moment, this research side, I would say, with very interesting questions and exciting, research. But on the other hand, you have this, say, industry-driven research. And then, as I said, at the moment, they are either interested in loose or very loose integration of sensing using radar sensors, so 77 gigahertz, I think. So this is a question we are confronted very often. So in this case, I don't know, I mean, probably there are no trade-offs. You buy the sensors and integrate this in the communication system. But in the standardization, to my understanding, is that, you know, you use this pilot signals, for example, in the uplink, but you can also do this in the downlink. And then, of course, OFDM waveform and channel state information and try to do sensing. And then I have to say that we can also observe the trade-off between sensing and communication. But it's not, you know, like I cannot quantify. Okay, I mean, there's this one work, related to monostatic sensing. And here we proved a bound. Really, it's quite practical because it's related to parameters like, for example, quantization noise. Then you have backoff or range of the AD converters. You have a peak to signal, peak to average power, you know, of the transmitted signal. I mean, all these parameters play a role when it comes to this trade-off. They have an impact on this trade-off.
Thank you.
Okay. If there's no question, I have one question, quite high level. So we know the research in this direction is prosperous, is very hot. I would like to ask, in your opinion, what will be the next step of to develop this ISAC, especially, for example, which direction or which directions will be the most possible ones to be standardized or to be really used in our lives?
So my opinion, of course, I mean, I think that we need this fundamental basic research because you don't know what the industry will be interested in 10 years. And so definitely from, say, funding perspective, I mean, at the moment, I think that we have to implement stuff and then convince people that this is a very important feature of 6G, right? So today I even, you know, was at the German parliament in Bundestag, and then there was a clear question, what is the difference between 5G and 6G? Yeah? And then you have, you know, like 10 seconds to answer this question. Yeah, I said it's an ISAC, yeah. And I said, okay, some aspects of NTN. They were very interested in NTN, and but we have to deliver. I think that there were some big projects in the area of ISAC, and not everybody is or was happy about, they say, the performance of suggested, say, solutions, schemes, approaches, right? So in the end, you know, if you talk to people from Bosch, I mean, they say, okay, I mean, what's the point? Nah? So that's why I think here we have to deliver, right? Because otherwise it will be like in the case of 5G. And yeah, so I don't know whether this is the answer to your question, but you know, it depends. I mean, I think basic research is another story. We have to, you know, push the theory. I mean, to better understand what are the trade-offs between sensing and communication. What are, you know, the optimal or very good waveforms under, say, practical impairments. Because just I cannot see, you know, these papers where just, you know, you use the whole old theory and you replace one bound, old bound by Kramer-Rao bound, but mathematics is the same. So from theoretical point of view, it's incremental or even, you know, converging to zero. And from practical point of view, it's also, you know, so that's why we need, I think, to incorporate practical impairments in the theory, right? Like to peak to average power ratio, I don't know, quantization noise, LNA saturation, and all this stuff. And then, of course, to get insights how to design. And then I think we have to observe what is going on in the standardization. Yeah, I mean, for example, they have this code book. They are designed for communication. But of course, I mean, for example, if you want to minimize the self-interference, then you want to redesign the code book, but usually you don't want to deviate too much from the code book proposed by 3GPP, right? So these are very interesting questions for us, but this is my perspective, more or less, yeah. Okay.
Thank you very much.